are given a singly linked list and a value x, what you need to do is you need to partition in such a way that all the nodes that come in the x first would be in the initial, and all the nodes which are equal to x will be in the middle, and all the nodes which are greater than x will be at the end. But there is one thing to note here, like suppose the given value is 3, so all the nodes less than 3 would be in that way. So that is 1, 2, 2 will be in that side, okay, in the first initial. But you need to preserve this ordering. You need to preserve 1, 2 and 2. You need to preserve. You can't write 2, 2 and 1 because this also satisfies the condition, but the relative ordering is not satisfied, okay? So you need to maintain the relative order, okay? This is how you need to do. So let us first see. So we have the number as 3. So all the values that are less than 3 are 1, and then we have 2, and then we have 2 itself. Fair enough? Then the next thing which is there is equal. So we have 3 and we have 3. So just count how many trees, it would solve the purpose, because in this we don't need the relative ordering, okay? Why? Because 3, 3, 3, the number itself, x, even if it is swapped, it won't make any sense. Now the values which are greater, that is 4, so 4, and then we have 5 itself, okay? So yes, we can see that these two are same. That is how we are getting the answer itself. Now let us discuss the first step. The first approach that comes in our mind is the sorting approach, okay? So we need to somewhat sort this, maintaining the relative ordering, okay? So sorting, but in terms of x, okay? We don't need to sort the entire linked list. Now sorting the entire linked list, we can think about the quicksort algorithm, okay? So if we are thinking about quicksort algorithm, we should also think about the partition function, okay? That partition function. Now in this partition function, we can use that as a pivot. So in the partition function, what happens? So we take any element as the pivot element. Suppose we have this array only, okay? 1, 4, 3, then we have. Now let us discuss how the pivot element, according to the pivot element, the elements are sorted. So in the partition function, we take an element as the pivot element. Here we would take the last element. So the pivot is 3 itself, this element, okay? Now what we would do is all the elements that are greater than the pivot would be after the pivot, and all the elements that are less than the pivot would be before the pivot, okay? So now let us first start the iteration. So we come across one, it is less than pivot, so we won't do anything, just we would simply move forward. Then we came across 4, so we would take out this 4, remove from here, and we would say stay here. Then we would come to 3, it is less than equal to, we would keep that, and then we would move that, less, we would keep that, then it is 5, so we would remove this, and then we would say 5 here, then we would keep this. This is how it is done. But as you can observe, the relative ordering is not maintained, okay? So this 3 is not here, okay? Even if this 3 was here, that means 3 and then 4. After this, we had this, okay? After this 3 was encountered. So even if we had the condition that all the less than equal to elements would be after that, greater than equal to elements would be after the pivot element, we would have this, and this thing is not maintained. And even if we try to maintain it by keeping less here smaller and here greater, okay, then we won't maintain the relative ordering. So we can see that the partition function of quicksort algorithm fails because of that relative ordering. Now let us see the sample test case again. Now let us see the sample test case, how we are solving it manually. So if we can see that x is equals to 3, so first there come the values that are less than 3, and we need to maintain the relative order. So we can see that we can partition that linked list into three forms. First, all the values that are less than 3, all the values that are equal to 3, okay, and all the values that are greater than 3, okay. And we are thinking of the same thing. So let us write smaller, let us write equal, let us write greater. First, what we would do is, we have encountered a value that is less. So what we would do is, we would do 1. Then we have encountered a value greater than 3. So we would write it here. Then we have encountered a value equal to 3. So we would write it here. Then we have encountered a value less than 3. So we would write it after this. So you can see 1 and 2, the relative ordering is maintained. Okay, we can see from the halfway only. Then we come across 5. 5 is greater than the x itself. So we would just write here 5. Then we come across 2, which is again this. So we would just write here 2. And then we come across the same element, that is 3. Now what we can do is, we can after this. So after smaller, the equal would be there. So we can join this and we would say that after this element should start. And after equal, the greater should start. So after 3, we would again join this. Okay, fair enough. This is the thing. So now we can do that. But there are some still more cases to be handled. Okay, so first we would do this, and after this joining, I would tell you some more things. Okay, now let us start the implementation itself. So we have smaller, equal, and greater. So what we would do is, we have seen that to join the end, we need the end and the head. To join the end, we need the end and the head. So we can see that we need to store the head and the tail of all the 3 linked lists. Okay, so what we would do is, struct node smaller head, okay, will be equal to null itself, and then we have the smaller tail, which would be again equal to null itself. So this would store the elements that are less than x itself. Next, we would just copy this line and we would change the name of the variable. Okay, so this is for equal and this is for greater. So we would make it equal head, and we would make it equal tail, and we would make it greater head, and we would make it greater tail. Okay, fair enough. Now what we would do is, we would start iterating on the linked list like we were doing. To iterate on the linked list, we would say that while the head is not equal to null, if the head has values, we would simply do that. And next, we need to iterate. So what we need to do is, head will be equal to head dash. This is just a way of iterating through the whole of the linked list. Now what we would do is, we would take out the value stored in the current node. So int val is equals to head dash val. Okay, head dash data itself. Okay, we don't want to write the same thing head of data of head. Now if the current value is less than x itself, so what we need to do is, we need to first check if the head is equal to null or not. Because if the head is equal to null, so if head is equal to null, we would simply assign the head. So if there is only one node, then the tail would also point at this and the head would also point at this. So what we would do is, s of head is equal to s of tail will be equal to head itself. Now if that is not the condition, if this thing is not the condition, what we need to do? We need to assign, see, the tail is now pointing at the end of the linked list and it has some values. So what we need to do is, we need to add one more element. So now the smaller value, that is 1, 2, there is something and we want to again add a value to itself. What we need to do is, and this is what? This is the tail itself. So we need to say that tails next would be now this element. So tails next would be now, and tail would be made to head. Okay. So what first we would do? First we would tell that tails next is this element, and then we would increment this tail. This is what we need to do itself. Okay. So we need to say that tail, small tails next is equal to head itself, and then small tail is equal to small tail that next itself. This is what we need to do. Now the next condition is else if the val is equal to x, if the current value is equal to x. So we have a separate, so the following procedure would remain the same. If equal head is null, then we would say that equal head is equal to equal tail is equal to head itself. Else the condition would again be the same, that equal tail of next is equal to the head itself, and equal tail would just move forward. Equal tail is equal to equal tail of the next itself. Now this is done. Now we would move forward, and the last condition would be if val is greater than x. So we don't need to do that because either it would be less, equal or greater. So we don't need to write it explicitly in else if. We can just write else. Now if greater head is equal to null, then greater head is equal to greater tail is equal to the head itself. Now the else condition would remain the same, that greater tail of next will be equal to the head itself, and greater tail is equal to greater tail of next itself. Okay, this is what we need to do, and now the three linked lists have been initialized. So now the first thing what we need to do is, everywhere it is pointing. So suppose there was only one element, okay, there was only one element like 1, 2 and 4, and then again 2 and then again 1. So now we were iterating over there. So now we came across 1. So 1 was assigned, then we came across 2, 2 was also assigned, and the x is equal to 3. Then we come across 4. So we would assign it to the greater value. But see, if we assign the head to this, then it would have the element next as this, next as this. So what we need to do is, we need to write the condition that greater of tail of next will be equal to null itself. Okay, greater of tail of next is equal to null. Now we would check the condition first, because null's next is null. So suppose there is no value that is greater than the current linked list itself. So we need to check if greater tail is not equal to null, then we need to simply assign that greater tails of next is equal to null. So if we have some values, we would do that, else we won't do that. Okay, now there are more things to do. Now consider the case when smaller, equal and greater. So suppose equal has some values, that is 3 and 3, and greater has some values 4 and 5, but the smaller is not having values. So what we need to do in this scenario is, in this scenario we need to first join these two, and then we need to return this one. Okay, this is the first scenario. Now the second scenario would be when not even this would exist. When not even this would exist, we need to return this head. So there are two conditions. If the smaller linked list, the linked list that is containing smaller values is not having any values, then we need to check if the equal has any values. If it equal also doesn't have any values as well as smaller, then we need to return the head of the greater. If equal has some values, we need to join this and we need to return the head of the equal. So let us first do this. So if the smaller head is equal to null, if the smaller head is equal to null, we will check for the next, that is equal head. If the equal head is also equals to null, then what we would do is we would return the greater head. Okay, if that is not the condition, that is equal head has some values, then we would say that equal tails next is equals to greater head, and we would return the equal head itself. Okay, the next condition is when the equal doesn't have. So if we are coming to the next smaller, equal and greater. So if we are if the first condition reverts to true, then only we would come to the next condition. So now we can safely say that the smaller has some values, and next condition we would check if the equal doesn't have any values or not. So the equal doesn't have any values. Now there is still a probability that greater does not have any values. Okay, so if greater does not have any values, it won't provide much issue. Why? I would show you. Suppose equal doesn't have any values. So what we would do is smaller end would be equal to greater head. Okay, and even if this is null, then smaller and tails next is equal to null, which is absolutely fine. So we don't need to check if the greater has any values or not. We would simply do that. And now if the greater don't has any values and smaller and equal has values, we don't need to care about that. Okay, fair enough. So now if not equal head, that is equal head is empty, then what we would do is smaller tails of next is equal to greater head. This is what we would do, and then we would return smaller head. Now if we have come to the end, that means smaller and equal has values and the greater might or might not have any values. So the first thing what we would do is smaller tails of next is equals to greater head. Okay, and then the next is this would be equals head, and then equals tails of next is equal to greater head, and greater tails is already maintained, and now we would return smaller head. Now that we have written the code, let us first compile and run for the sample test cases, and then let us submit this. So let me see, and yes, it is working fine for the sample test cases. Now let us submit this. And yes, it got accepted. Thank you and have a nice day.